Alright, so most of this unit we spent learning how to figure out the shape of molecules. In particular, the shape of how atoms arrange themselves around some atom of interest. Okay, we talked about a tetrahedral arrangement, or a trigonal planar arrangement, or a linear arrangement. And the tetrahedral can become, if you have lone pairs somewhere, and you have to eliminate those before you get to that molecular shape, you can get out of that tetrahedral arrangement of bonds, you can get a trigonal pyramidal shape or a bent shape. We haven't shown it in this class, but out of a trigonal planar shape, you can actually get a bent shape as well. If you have a lone pair in there somewhere, you end up with a bent shape. And anytime you have two sets of electrons around a central atom or atom of interest, you get a linear shape every time. We talked about that. We practiced with that. We spent a week on that. Okay? So what I want to talk about now is the structural arrangement of ionic compounds. So yesterday, we spent some time practicing figuring out the formulas for ionic compounds. We did that with homework. We went over it again. But I want to talk about the structure of ionic compounds now and how we get that structure. It's up to you. Here's a new page if you want to. So I'm going to do something really, really simple because we're not going to get into a lot of detail in this class about the different kind of structural arrangements. I want you to know in general, the kind of structural arrangement you make anytime you have an ionic, almost any time you have an ionic compound. Okay? Not every single time, but almost every single time. Okay? So let's look at a really simple ionic compound. Can anybody think of a really simple ionic compound? H2O is covalent.
Table salt. No, like salt.
Table salt is ionic compound. Okay? There you go. Sugar. Sugar's actually covalent. All right. So, what is the formula of table salt? Oh, y'all know that. Good. All right. Well, if NaCl is an ionic compound, what are the charges for those ions? If it's ionic, it's got to have charges. That's why we call it ionic, because they're ions. So what's the charge on the sodium ion? What is the charge? Everybody should be looking now, trying to find it out. What's the charge on the sodium ion? Somebody shouted it out. They said it's 1+. Is he right? Well, make sure he's right.
Yeah, 1+.
Okay, good. Where'd you find that out? Periodic table of oxidation numbers. Okay, it's part of your references. What's the charge on the chloride ion? -1. Why is it not 5+ or 6+? It's not a matter of being the most common. Who said balance it out? There you go. You got to end up with a 0 charge overall, and the only way we can neutralize a positive charge is with a negative charge, and the only negative charge on chlorine is 1 negative. Okay? So a sodium chloride formula is made from a positively charged sodium and a 1 negatively charged chloride. We call it chloride when it's a negative monoatomic anion. Okay? A monoatomic anion has an IDE ending. But they don't actually arrange themselves as one sodium ion and one chloride ion. Okay, those don't just bond together and that's it. Doesn't stop there. Okay? What actually happens is that you get lots of these. So they have another sodium ion sticking up against this chlorine, and another sodium ion sticking up against this chloride, I should have said, and then more chlorides here, and here, and here, and here, and then more sodiums. You are writing all this down, right? Good. It was like a what? Like a pool table? The way you arrange the balls on a pool table? Yeah, kind of. Okay, we need to have less chatting about extraneous stuff and more if there's any talking at all, focusing on chemistry. Yes. No. These are monoatomic anions and cations. Cation, anion.
But NaCl is poly.
Well, you don't usually refer to this kind of structure as being polyatomic. It is, but polyatomic is something you hold on to and use only for ions. And these are not polyatomic ions, they're monoatomic ions.
I don't have that many.
So what was that?
Monatomic ion.
It's an ionic compound made of monoatomic ions. Okay? But now this is two-dimensional. And just like our molecules, just like those structures we drew for the shape of bonds around an atom of interest, this is also not going to be just two-dimensional. Behind this sodium is going to be a chlorine. Behind this chlorine, a sodium. Behind this chlorine, a sodium. Behind this sodium, a chlorine. Chlorine, chlorine,
They're all just kind of like,
sodium, sodium. Huh?
they're all just kind of packed together.
They're all just kind of packed together.
Into a cube and salt.
What'd you say?
Into a cube.
Into what? A cube?
Oh, thank you.
Imagine that.
Somebody just cut a cube out of the
All right, so if you use that viewer that I gave you, you should be able to see the shape. All right, everybody got that? All right, make sure you draw this illustration in your notes. And, listen carefully, and if you don't know how this happens, ask Davia since she figured it out. And write an explanation of why the notes we did a moment ago, showing the way that sodium and chloride arranges itself, ends up being, when you've got billions and billions of those ions, this shape we're looking at right here.